So big pictures, I really don't care to be punitive when it comes to grading. I just want to make sure this gets online. It should. There we go. Okay. I don't want to be a punitive person when it comes to grading. I want it to be there to make sure that you can see what you're learning and where you might need some help. Because ultimately, I'm going to tell you all this stuff and I can give you help with all this, but ultimately when you go down to do it yourself, it's hard to do, right? So, are we cool with that? I want to give everybody an A. At the same time, there will be ways to improve your grade. So, like I feel bad for assessing you at the same time. I know it's important, right? It's like when I feel bad for my toddler at home wants to, push the limits of boundaries or whatever, but I know I need to set them. So anyway, 3 points. Let's talk about last time. So I gave the classical test theory lecture that everybody's like, oh, here we go again, right? Because all of you have taken classical test theory, and I'm sure that you'd have loved it. Speaking of, before I do that, Jesse, could you get the door, please? I don't want to speak ill of it in front of my colleagues. Classical test theory. But no, as I was giving the lecture, I was thinking the same thing. Oh, here we go again, another classical test theory lecture. But on the spur of the moment, I tried to turn it into something that was a little bit different. So just sort of my take on it. So validity, let's talk about that. We started with, there were some slides on validity, and I'm like, the problem I have with validity is that it always starts with the score, right? And they never check anything that goes into the score. It's just like the score is like your height or like something that's measured perfectly, and after that comes validity. And to me, validity starts with the process of understanding what the score has to be, right? So I would talk about that as prerequisite validity, assumptional validity, and I try to put the parenthesis there to really kind of elaborate what I was talking about. So if you pick this answer, right? But does that make sense? So in the big picture, though, when I mentioned this last week, nobody seemed to. Has your experience been nobody really talked about the process of up to the score? It was just the score. It exists. Ta-da! Right? Like, and to me, it's like what you're going to see in this class from now on seems really, really complicated, but all it is trying to get you a better score. A score that you can believe the numbers in, and believe the ordering in, right? And so it's essentially a whole class on validity, although you'd never call it that. I'd probably never call it that. I used to say those who can do and those who can't do validity. So,
yeah. I'm not sure if this is right, but I can relate what you are saying to what MISC have proposed, like since the 90s.
Yeah, Ms. Levy, yeah, with the ECD.
Yeah.
Yeah, with the measure model, the student model, and the task model.
So his way of the idea of integrative validity, which include all aspects of validity together.
That's good.
Before doing what you are doing, and it check, okay, what's the and it's a process not before the administration or building the estimate, but also after.
That's right.
We check before and after.
That's right.
And during.
Oh yeah, and the other thing I wanted to mention about it, so it may be much like that. Although, there is sort of an interplay. You check your task model and you see. I'm not an expert on ACD, don't get me wrong, but it's a thing that you have to do it. The other part with it is that a test. I don't like the word validated. Right? Oh, this test has been validated. Ultimately, because the time that you gather evidence for validity was a different sample altogether, right? So if you're going to say I'm using, pick a test that you like, the MMPI, the BASC, the GRE, it's been validated. Well, that doesn't mean that the person who's going to walk in the door and answer the questions it's valid for, right? So I don't like to use, the test is never validated, right? It's always something that you have to go and check and see. Exactly, yep. So the answer to number 1 is A, and is there anyone left? Could you pass one down? The answer to number 1 is A. So these are 3 points on the quiz. So, any questions on that? Any thoughts? Awesome. So number 2, we mentioned there was all these reliability formulas, but I don't really want you to keep track of all of them. Actually, what I'm going to teach you in CFA, there's one formula if you add up the scores, and there's another formula if you use the factor score, right? And that formula, if you add up the scores, sure enough, if the assumptions of alpha are met, it's going to be alpha. And if the assumptions of Spearman-Brown are met, parallel items, it'd be Spearman-Brown. It actually subsumes both of them. So with one formula, you can do it all. They're all on continuum. So I don't want you to think about the reliability as a formulaic approach, but I want you to think of it as a concept. What does reliability represent? And that's where that ratio I put up on the board was, right? It's the proportion of total variance that's due to variance of the trait, right? Or variance of the trait divided by total variance itself, right? And so regardless of the name that you've used in a reliability statistic, it all boils down to that, right? Even though it may not feel like it, because oftentimes we say, there's reliability, and then we give you this complicated math to give you the formula for it. That's all it's trying to do. Proportion of variance that you see that's due to the trait. Yeah, Jesse.
So in classical test theory, and I know you got into this in the lecture a little bit last time, but we talked about true score variance over observed score variance.
That's right.
Is that the same
Right.
idea that we're getting across?
The only difference I'd say is true score really gets what we call trait variance. That's
Sure.
right. Yeah, in classical test theory, it's the true score. In these other frameworks, it's another thing, but yes, that's exactly it. When you have reliability, it's the variance of the thing that you're trying to measure over the total amount of variance that you observe. Now, the other part why I say that and why that's so important is that you're going to quickly move into places where the total test score, the summing up of items, the sum of questionnaire responses, isn't valid. It's not a valid response at all. In fact, I'm going to show you that some of these lectures on CFA as we get into it. Believe it or not, the process of summing items, you're treating all items as interchangeable, right? That's right. That prescribes a very, very specific type of model, one where the variances are all equal and the relationship between the item and the trait are all equal. A model that never fits data. And so what happens, you'll get a high correlation of that sum score with the trait score if your dimension is unidimensional, right? If it's truly there. However, what's going to happen is you start to see a bunch of people reverse order, right? This is particularly important because we're trying to think of measurement as something that's this idea that if we have perfect measurement, people are on an interval scale. We shouldn't see people who are, if I'm a 7 and Jesse's a 6, when we add things up, we shouldn't see Jesse become an 8 and I become a 4 when we go through the trait score when things aren't equal. So that's what's going to happen. So it's an interesting part of things that happen. That has ramifications for what you do with people once you give them the score, but also has ramifications for what happens to your statistics if you use that score again. So that's just something to think about. So why I say this about reliability is that's the concept. The question is reliability for what, right? And I don't think people understand that because there's multiple versions of how we give scores. There's the classic way of summing things up. And then there's this new way that's going to be factor scores, or essentially factor scores that show up. But each time when we want to quantify it, whenever we produce a score, either to use in another analysis or to provide to a client or a person that we're talking to, reliability has to correspond to that score. Sounds weird. I know you're probably not knowing where I'm going with this, but in my backstory, what I typically see is you'll have people who are like, well, hell, I brought up the GRE the last time. If you look at the GRE book, the reliability they quote you over the whole test is something for a sum score. But the score that they give you is a factor score, right? That's not congruous, and they're not comparable, right? So that's part of the issue. Interesting. Okay, could you pass those forward, please? So did everybody get the answer to number 2? Variance of trait over variance total. So I hate to violate privacy in this class, but now you know each other's grade. You're all 100%. But, thank you, Naomi. So were you able to stream the class last
Yes. Yeah, I could hear you very well.
That's awesome. I'm glad to hear that. I'm still learning this whole thing. I'm old, but I'm not as old where I can't start using new technology. So. Okay, how's it going otherwise? So how's that for a quiz? I want to give you as many points as possible. I really do. I just, All right, I got to get over myself. Okay, we're all okay with it, right? Everybody's going to do well. All right, good.
We appreciate the small portion of technical analysis.
Well, it's more just trying to, honestly, you're all in grad schools. Ultimately, we're going to, whether you get a B or an A, it probably matters little, but to to motivation, I think it matters a lot. And I want to treat you more like a peer, but at the same time, I want you to be able to see where you need self-improvement on certain things. So today, we're going to talk about confirmatory factor analysis. And this is lecture 4. But lecture 4 is going to span at least 2 weeks, probably 3, potentially 4. Because there's a lot to this lecture, let me tell you, because, so again, I'm doing this weird thing this year where I've decided to, like I have, my version of SEM is up. You can see on the website I put up other material, my lectures from other classes and so forth, where you can link to it and see them in different ways. And if you go and click those, you'll see I taught it very differently the last time I taught it. And I'm doing this, I'm basically using Lisa's materials for the most part, but adapting them to R and then sprinkling a few concepts in, mainly to try to be more homogeneous between the cross-listed classes, but also she's got more of the important material, which are what happens when we don't have continuous data. And in doing that, she does lecture PowerPoint, so lecture slides, but also she has examples. And I have taken the examples and converted them to R using R notebooks. So what you should be able to do is download or go on the website and you should be able to find an R notebook to download. Now the example data itself is real data that we can't just distribute. But if you go on the website, so first thing first, I will be jumping between the example and the slides to try to make a point and then go show you how to do it in R. So if you have your laptop here, now would be a great time to start R and to install the package named Levon while I talk about it. So I'm kind of going on thought path. So when you start R, there is a function named install packages. And so if you run this function right here, as long as your computer is connected to the internet, it will start the process of installing Levon, which is the package in R that we're going to use. The function is called install packages. It's all install.packages. It's all in lowercase. And then in the parentheses, in quotes, you put the word Levon, L-A-V-A-A-N, all lowercase. And as you're doing that, I'm going to pull up my website. And here we are, example 4. So the real data notebook is right here, this link. And that's what I'm going to be using with the class. But if you'd like to try this for yourself, I created simulated data in a notebook. And you can click on that link. I'll show you this. Now the numbers are not going to match because it's simulated data. But if you want the code, if you click up at the top right, you can click download RMD. It'll download the syntax for you. And then each of the sections in R you can run simultaneously if you have RStudio. Any questions on this first of all? Anybody have health problems getting Levon? You should see lots of things installing. It installs like 18 packages. Cool. If you have questions, now's the time. My goal in teaching you this is to get you to use it. So, yes, Maya.
It showed up in this section. How can I?
Okay, so that's the next step. Let me just show you what to do once you download it. So if you download this syntax file, and you're in RStudio. Now you have to have RStudio to make this work. Everybody have RStudio? No. You can download it now. You don't have to.
It's not free, is it?
It's free.
RStudio's free?
Absolutely. It's been always been free. The cheap version, there's like a no support.
Oh, there's a version for that.
Yeah, there's more versions that you can pay for, but
I'll follow along.
gotcha. Once you've downloaded this file, the next thing to do is to go up to this Run button right up here. And when it drops down, what you're going to see is the Run All command. Run everything. What that will do is put this little progress bar down in the bottom left. All right, so what it's doing, what this R notebook does, there's a bunch of text here that gets marked up or marked down give you this window. But it relies on syntax. And then, if you want to see it in the window, you click the preview button right here. And then what you should see is in just a moment, it pops into the window, the viewer window. It may pop up a separate window separately. If that's the case, but you want to see it in the view window, if you go to the little wheel button by preview, you can say preview in window pane as an option, and it will put it right over here in the viewer, all in our studio. Questions? Does anyone need help in trying to see how this works? Okay. The other part that this does in the actual text part over here on the left, if you scroll down, what you're going to see is right beneath the R syntax. You'll see the R syntax is sort of colored in a gray, and in the top right there's a run current chunk button. That will just run this part of the syntax, and you'll be able to see what happens. So down here, for instance, when I go and get the correlation matrix, it shows up right below the R syntax. So I'm going to try to teach this a little bit more interactively. Now you can actually change the syntax in here if you like. And you can try your own syntax, push the play button, and it will just re-spit out new things. So I'm going to see if this is my first time teaching from notebooks in R. So I'm hoping this gives you a little bit more interactivity with some more description around what happens. But we'll see.
I don't know if anybody's having trouble, but yeah, error.
So when you see that error, try the run button again, and click run and go run all at the bottom. And then when this is all done, that error should go away. What happens when that error, if you get a little error that pops up, by the way, I learned that this weekend too. So when you get a little yellow thing that says something not found or object or something like that, that really means it can't find one of the pieces of the syntax in the environment that it's in, like in its memory. So if you click run again, that should remove the error eventually.
Sorry, which document is
The syntax is, go to the website.
Yeah.
Oh, I should get on the website. It is, the syntax to try yourself is this R notebook with simulated data. The one I'm going to be teaching from is the R notebook with real data above it.
So which one should we use?
If you want to play with it yourself, go with the simulated. If you want to see the actual numbers I've got, go with the real one. But this one you can't run yourself. You can just see the text. Okay. Okay. Other questions? The one thing I'm very happy with is that you're all at least familiar enough with R. You've gotten over that terrible learning curve enough to be like, okay, I can open it up and at least have a shot at this. Does anyone struggle with R still? I do.
If it opened up the
Okay, if you want it to not do that, if you go over to the RStudio window, and then there's this options wheel that's right by preview, go to preview and viewer pane. And there you go. There it is.
I look professional.
Yeah, well, I like it all in the pane too. I don't know why the default is to pop up a separate window. Okay. Other R questions or things to think about? No problem. I have a love-hate relationship with R, really. I've started to love it more now, but it's only because of years of trying and failing. So I don't expect you to try and fail as long as I have with it. So if you're in that spot, it's okay to be there. I'm here to help you. Also, we have a visitor today in the back. That's our teaching assistant. Lou is back. And I would say to email Lou also if you are trying to do anything in R. Try emailing her first, and if you both can't figure it out, then I can help as well. Because Lou's job in my mind for this class, because it's 900 level class and I don't want her grading your papers. I'm grading. She's tech support. That sound cool? Okay, cool. Shall I begin the lecture? Okay. And if at any point you have questions even about R, just stop me. But today we start with a comparison of EFA and CFA. Oh God, make it go away. EFA. This is on YouTube, yep. It should be. Oh, come on, template. That one right there. Yep, I'm live. There we go. Okay, so first of all, the difference between the two. What gets analyzed in EFA versus what gets analyzed in CFA. Oftentimes in EFA, not always, what we see is analysis of the correlation matrix. This is in the roots when we talked a week ago on the deal. I think Jesse asked a question about the Kaiser, or maybe made a comment about Kaiser criteria and why the value of 1. Well, 1 is in a correlation matrix the contribution of each variable to the total variance. So in CFA, unequivocally, we use a covariance matrix. Technically speaking, we use the raw data. Now, again, I mentioned last time why that's the case. Do you remember? It had to do with multivariate normal. And the multivariate normal, what's that?
You have a vector of means and you have a covariance.
That's exactly right. The two statistics that describe the multivariate normal distribution, the two sets of matrices of statistics, the mean vector and the covariance matrix. And ultimately what we're doing is we're not actually going to, now, way back in the 1970s, when Lizerl came around, or when you were doing EFA, what it would do is calculate the covariance matrix and then shoot it into the SEM machine, or the CFA machine, and out would pop results. Right? The same thing here in EFA, you create a correlation matrix and then shove it into the EFA machine and out would pop results, right? We don't do that anymore for a number of reasons. The main one is missing data. We instead use something called full information estimation for the continuous responses. When we have a CFA model where we're assuming all the items are continuous. Full information just uses the raw data itself, right? So while what's getting analyzed, we say is the covariance matrix, really the model is implying a very specific structure to this covariance matrix. Meaning, if you say there's one factor, the covariance matrix should look like one factor. I'll show you what that looks like in a few slides. Right? If you say there's 2, it should look like there's 2 factors. But this is essentially what happens. Now, the covariance matrix itself, this full information approach is better because of missing data. In particular, when we use maximum likelihood-based methods, which we'll use in this class exclusively for CFA, we get this missing data protection called missing at random, which just means that the missingness that you see is related to something in the data that you've already collected. So essentially, it's a little bit better protection of missing than what would happen if you gave it a summary matrix and you decided to pairwise or listwise delete data that might be missing. So that's why we do full information methods these days. So full information, what that really means is we're not creating a summary statistic and shoving that into the program. We're just giving the raw data. Questions? Yeah, yes.
I'm not much of an expert at all on missing data, but expectation maximization is one methodology I'm familiar with.
That tries to fill in the data.
Is that different from what ML does?
Imputation is, right? So EM, what typically would do in an EM process, and some of the CFA programs will do that, but all the missing data, basically, you have a model for what the data should be, right? Conditional on the factor, you know what each data should be. It basically plugs in what the mean should be for that piece of data, and then goes and uses it as with a complete data file to maximize it. What ML also does, another way of doing it, is to not impute at all, not plug in a number for the data. It skips it, basically, right? So if you have, let's imagine like today we have a test with 6 items, a questionnaire with 6 items. The covariance matrix would have, it's a 6x6 deal, right? With 6 variances and then 6 choose 2 covariances happen to be, and there'll be 6 means the mean vector. If you have a person who only took 5 of those items, it drops those components of the mean vector and covariance matrix to shrink it. So effectively, we use all 5 that they took and skip over the 6th. And so the model-based imputation and the model-based missingness should start to give you the same amount of, same results, so long as EM actually isn't being used, if you use some type of stochastic imputation. The problem with the EM version of for imputation is you're plugging in a constant value for each person, rather than allowing it to wiggle, and so it could bias the result. And actually biases the standard error more than anything else. It makes it look like you have less error than you really do. So other questions? Okay, so what we're going to see in CFA is we'll get a bunch of output that's on the scale of that we were talking about last time, which is the scale of the data that you have, right? So things will be like regression coefficients will be in units of the variables, the Likert units that you use most often. But that's what we call an unstandardized solution. There are other versions of standardized solutions that we will also see, and those will be as if we use the correlation matrix. It's essentially allowing, remember we talked about the process of standardization last time, we remove the units from it, right? We basically give everything a standard deviation of 1. And in that case, if every variable has a standard deviation of 1, the covariance matrix is the correlation matrix. So that's what I think. Interpretation coming up next. You know, EFA, if you don't like your solution, rotate it. We talked about our favorite versions of rotations the last time. My favorite is none. CFA, you need to figure out what the structure is in the first place. It's a hypothesis test, right? You're hypothesizing this survey fits the design characteristics with which you use to build it in the first place. And then you are trying to reject that hypothesis, essentially. Actually, you hope it's not rejected, although you can never prove a null. You hope that if you reject the hypothesis, you know that it doesn't exactly fit the design, the structure that you think it is. You have to essentially modify the model, which blurs the line between CFA and EFA, right? You're sort of exploring it a little bit, but it also gives you some more information with it. So by specifying things, you have to specify the number of factors that you have. You have to say that they're correlated, or maybe they're not, if you don't think they are, although I rarely ever see that part.
Like the factors themselves.
Yes. Okay. Generally speaking, we specify the factors, and we just assume they're correlated, and we estimate all the correlations between them. But we don't have to. If you have a theory that says there's no correlation between this and that, you can shove it in the model and test it. Second, you have to figure out now which items load on to which factors. Right? So you say items 1 through 6. Like what we're going to see in our example here, we have 6 items. We assume there's one factor, so all 6 items have to load on the one factor. Right? If one of those items weren't to load on that one factor, we would just kick it out of the analysis altogether. Go. And you also have to specify any additional relationships for potential confounds that might be present. We talked about before, things like negatively worded items, which we're going to see in our example today, or other terms that might pop in that might otherwise effectively weaken the measurement argument. It somehow threatens model fit. So you essentially say, these two things are more related than I expected them to be, and I don't know why. But we'll get to that down below. So there's more things to specify. Typically, this last thing shows up when you've exhausted every other way to try to make your model fit. You've got a good, valid reason for why that is. I'll show you examples. Now, how do we do model fit? In EFA, eyeball, opinion, sorry, scree plot. Yeah, I didn't even talk about that. You know what scree means, right? Okay, here we go. I'm glad, was it Catherine? Katie, I'm glad you said no, because now, as a quant person, you live for this day. I wish I could do it here. Let me see if I can do this. Okay, Google. Define scree. Oh, not scurry. Define scree. A mass of small or loose stones that form or cover a slope on a mountain. It's thought of as, if you have a cliff, it's the garbage that's fallen down at the bottom here. That's a scree plot. That's where the name comes from, right? You're sort of looking for the elbow. Where's the garbage? Yeah. That's why a scurry plot. Scurry, yeah, a scurry plot sounds better. Scurry. But yeah, seriously, which value of discrete plot are you going to pick? Which rotation? Which items load on which factor? Where's your cutoff? You've sort of got proportion of variance accounted for, but that's only if you don't use the maximum likelihood version. And if you're not using that, what are you doing? It's a mess. But with CFA, what we end up getting is some inferential tests, some actual statistical hypothesis tests when we use maximum likelihood, which is our method. We also have a robust version of maximum likelihood we tend to use always in CFA. But it's maximum likelihood, but it provides a little bit of protection if your data aren't exactly normal. We'll get into that coming up too. But the inferential tests that you're going to find are a test of global model fit, like an actual hypothesis test, like with statistics and everything. But you'll also be able to determine from that some versions of local model fit, meaning where is the misfit happening, or where is the fit good in my analysis? Like which item or which pair of items do I need to modify when things don't work well? You'll be able to talk about, instead of figuring out if your factor loading is above 0.3, you can talk about actual statistical significance of the item, the factor loadings. You can talk about the significance also of error covariances or variances, although we never talk about variances for significance tests, we rarely do. But you can also test the appropriateness of model constraints. So for instance, one of the things you'll see in our example is us testing whether or not we should add up the items altogether. Okay. We can go and plug in the constraints that would give us the classical test theory version of our model, and we can test whether or not those fit. We can falsify it. We would actually reject that hypothesis almost all the time, but we can do that. So there's all sorts of more powerful things that you get in the CFA. Factor scores in EFA, they have an issue with rotational indeterminacy, meaning they're only unique. They're not unique. When you use the rotation, you rotate the scores too. In CFA, you can use the factor scores. I would say only if necessary, but you can. The best option is to use, if you're going to use the factor scores in another, if you're going to report a score to a person, yes, the factor scores are fine to do that. If you're going to use the factor score in another analysis, basically, you want to see if men and women differ in their levels of tolerance for scree, right, or whatever it happens to be. That's what structural equation modeling is for. You don't output the score at all. You build the measurement model, you build the CFA model into the analysis, and then you build in the test to compare the group differences. And you test it directly in the analysis itself with no outputting or anything. And that actually protects you much better, because when you give a person the score, that bit of the score that you're calculating the reliability for, 1 minus the reliability sticks with it, right? The error comes with it. So anytime you give a score, probably shouldn't, unless you're somehow, if you're going to use it in some other type of statistical analysis, you want to somehow account for that error. There are ways that you can do it when you output it, but ultimately you can't do an FCM in every context that you do just yet. And we'll talk about those in the SCM part of the class. Yeah.
Actually, this is the question that I was thinking about.
Mm-hmm.
You mentioned test out. Why is there like great deal of indeterminacy in the
EFA?
EFA and less indeterminacy in
In one regard, it's because the CFA, we don't rotate the solution. So whenever we say the EFA scores are indeterminate, there's what we call rotational indeterminacy, meaning, if I do an EFA and I use Verimax, but Craig does an EFA and he does oblique, Oblemin, something like that, and Jesse does Geomin, all of our scores might be different, and depending on, all of our scores will be different, number one, and depending on the software you're using, some of those rotations cut off, like have error in it also, so there's even more issue with the process. That's the big difference. What's present in both, for what people have lumped into indeterminacy, is reliability. When you have a score from a CFA, if you're going to give a factor score, that has a reliability to it, which means that number may not be perfectly reliable. and there's error due to that reliability. And when we get to the score part of the class, I'll get to saying, like, I think of scores oftentimes in what we do in most contemporary versions of measurement. If we're giving people scores, we're using Bayesian statistics to do so. And really what we're talking about is characterizing a distribution of plausible scores for a person, right? If the score is perfectly reliable, that distribution is straight up and down. If it's not, it describes how wide that distribution might be. And that's the issue with another version of indeterminacy, which people have lumped in. I just call it measurement error. So, does that help? Yeah. Thank you. Okay, other thoughts, questions? I get really riled up with this. I'm excited. Okay, that's factor scores. What does CFA look like? I drew this. We talked about this before. But here, for each item in the assessment, the test that you have, we're providing a regression analysis. If that regression analysis, if you're only measuring one trait, and this item is only loaded onto one trait, say it measures one trait, you get a formula at the top where you say the item, this is for item I and subject S, is equal to parameter mu, which is the model parameter, plus a lambda, which is a factor loading. And you'll see the subscript I on both of these means each item gets their own unique version, times a person or a subject's factor score F. That's the thing we didn't observe. That's the trait. Plus error. Right? So it's regression. Essentially assuming, had we observed this person's trait, we could go and talk about how well that trait predicts their response. Right? If the trait predicts the response with an R squared of, in regression we talk about R squared proportion of variance counter. If that R squared is 1, that essentially means that there's no error whatsoever. There's no measurement of error in the item at all. Whereas somewhere less than 1, you're going to have some type of unique variance that we have to estimate as well. So once again, mu represents the intercept of the item. It's commonly going to give you the item mean back. Lambda is the factor loading. It's the regression slope. So if you use the raw data, right, you're not using anything but, it's on the scale of what? Lambda is a regression coefficient. It's units of y, right? So this is a Likert scale item. It's how much of the next option are you going to pick, right? Per unit of the factor, or per standard input. So that's how we look at it.
So for each item, it is like a mean in the case that a predicted mean in the case that the lambda is not lambda, like that in the absence of the traits.
That's right. That's right. What this mean represents exactly if your trait value is 0, what the predicted response would be at a trait value of 0. The absence of trait. Other questions? So I won't make you answer the questions at the bottom there. So if we revisit vocabulary, this is the end of the classical test theory lecture. I said there's these two parts that we see show up again and again in measurement models. And one was discrimination, how well an item discriminates. In classical test theory, we often quantify this with the item total correlation. And there's 18 versions of how that is doing. So there's two, right? One with the item in and one with the item out. I don't need to get into that. In CFA, discrimination is calculated by the slope of factor loading. Right? Because a bigger version of the factor loading means the more the factor goes up, the more the response goes up, or vice versa. We haven't talked about that yet. It has a metric. We have to pick the metric for it. Standardized is one way, where we pick the mean of 0 and the variance of 1. In fact, that's where we're going to start. So you can think of it that way to begin with. We're quickly going to see that we're going to run into issues in SEM if we do it that way. The models are identical, however you choose the mean of the variance. But describe more of that later. So yes, discrimination is calculated by the factor loading, or the slope. When we get into item response theory, it's still the slope. Although we don't call it slope and we don't call it factor loading, we actually call it discrimination. Next, difficulty. In classical test theory, we talked about that being the item mean. We also talked about it being flipped, right? If you talk about a cognitive item, like a test item, like the quiz items here, the proportion of people who answered that right is the item mean. The higher that proportion, the more people got it right. The less difficult that item is, but we call this difficulty instead of easiness. In CFA, the analog is the item mean, which is often indexed by the item intercept. And I say often because there are times where we want to change the scale of the factor to have a factor mean different than 0. And that changes what the item intercept represents. It's no longer the mean of the item in that case. But also, in contrast to other versions of these types of models, other latent trait models, measurement models out there, the item intercepts get ignored in CFA, almost always. There's two reasons for that. Number one, we often say that every item gets its own, which is like saying every item's mean shows up. So in that multivariate normal distribution, there's a mean in every mean, the right mean goes in every spot of the mean vector. It fits perfectly. The other part's this. Here's a plot of our item response function. If you take the latent trait or the factor from low to high over here, and the value of the predicted response, right? This is given by this part, mu plus lambda f times f. Right? If you take a look, the item intercept represents the part where this, if this is 0 for the factor, represents the part where the line crosses at 0, crosses the y-axis. And this steep line right here has a bigger slope. This flat line actually has a 0 slope, right? But it has a higher intercept. Right? The reason why we ignore this effectively is because the intercept in CFA is independent of the slope. It doesn't tell us anything about the quality of the item. A bad item may have a really high intercept. This item, though, with a 0 factor loading means it doesn't measure the trait at all. There's no predictive ability. If you knew a person's trait score, you'd just pick the mean effectively for the item. Whereas this one has a low intercept, but it's a really good item. In fact, that looks like it's perfectly related. It's almost like whatever the correlation of one analog of a regression slope would be when you add the units back. So, what do you think? Questions? Deep breath. I talk quite quick, but hopefully if you need to hear this again, you can go back to the lecture online and it's there. So what happens in CFA is we often use a path diagram to describe the CFA model. And the quantitative psychologist in me and the person who does statistics hates these. But they're really pragmatic. Because what they do is they take a very complicated set of equations and try to make it a visual display for what you do. What I dislike about it is that not every term on many of these in the model shows up on the picture. Right? So they're not necessarily, we wouldn't say they're isomorphic with the model. It's a schematic display of the model itself. There are ways with path diagrams, like you can with any other visual tool, that you can hide things that you don't want people to see. Right? But I think these are very good at imparting information. What are we looking at here? When I first saw this, by the way, I was like, what the heck is this? Like, I landed on Mars, and whatever inhabitants of the planet, this is like the language they spoke. You ever feel that way? For those of you who probably aren't from the United States, they probably felt that way when you came here the first time. What planet am I on, right? Anyway, I'll stop there. It's also true when you live in different states of the United States, and you go from I'm from California, but I've lived in Illinois, Nebraska, Kansas, and Georgia, right? So that's a number of places to live in different places. Anyway, different planets altogether, right? Let's unpack this a little bit. The circles represent the latent variables, and in this case, sometimes we put them on error. So this over here, this is factor 1. And this is factor 2. You see the circles are connected by an arrow that has, or by a line that has 2 arrows to this. We call this an undirected path, which means there's correlation between the two, but we're not implying that one causes the other, or vice versa. Now mind you, even if we implied that one caused something, causation, if the model fits, causation is but one reason why. It's not necessarily. Causation is something you have to do through design. You have to actually manipulate the levels of the factor to be able to say that. But anyway, this is a covariance. It basically says these two things are related, and I'm not explaining why, but they're just related. You'll see coming from the circle down to the box, the squares, those things are the observed items. Right? So you have y1, 2, 3. Whenever you see a line from the circle down to those items, you're saying this factor is measured by those. And you'll see there's one point to this arrow. It's a directed arrow, which means values of the factor as it goes up or down imply values of the score go up and down too. Yes. Sorry. Shada. Thank you.
In the triangle at the bottom,
yes.
where it says 1, is that like subject 1?
No, I'm going to get there. That is what we call the mean structure. So path diagrams came out before we were really doing mean structure models, and this is sort of their band-aid to try to make it work. But we'll get to that in just a moment. That's this odd thing. Oftentimes in most models that you see in practice, they don't have this. Mainly because what this is implying is that each item has a mean, and to get that mean, we multiply it by a 1, and it says that item has a mean. Have you guys, I'll say it now. So this is the description of that. This is the mean structure. It says basically 1, 2, each item has a line that comes from this, and the factor may have a mean as well. Have you seen on the back of the US dollar bill, there's the eye in the triangle? This is what makes me think, you know what that's called? The eye of providence? I've heard this before. I don't know, there's some, here, I'm going to be like a conspiracy nut. Oh, it's, some Freemason thing. No, I'm just kidding. It's some, I don't know, historical deal. I don't even want to look. I'm not going to ask. Actually, yeah. Okay, Google. Define eye of providence.
According to Wikipedia, the eye of providence is a symbol showing an eye often surrounded by rays of light or a glory and usually enclosed by a triangle. It represents the eye of God watching over humanity.
Okay, so that's what that is. We're getting biblical on us here. Regardless of what your belief in the deity of your choice or none thereof, that's what this reminds me of. It's the all-seeing eye that shows up in the back of the dollar. I don't know. It's just we started running out of places to put things. This is the problem with the diagrams. So
in most models, it won't even have like the one at the bottom and the. Okay.
Yeah, most of the stuff that we're going to worry about in the model comes from the parts with the circles and squares. See you, Jesse. Okay, so here, once again, factor. The line with the arrow, people would say you're implying there's causality, meaning higher a person's factor or lower, it has an impact on the item itself. On the other end of it, there's error, which is enclosed in a circle sometimes, but not always. Meaning we didn't directly observe it, which is true. We have to observe the factor too and whatnot. People have some nasty knockdown, drag out battles about how to draw these things that aren't really real. And it also shows up. So it's like, what goes into each item response? There's a factor, there's a mean, there's error. That's what it's trying to do. You'll see that the first 3 items have the arrows coming from factor 1. That means they measure factor 1, but they do not directly measure factor 2. Now you note my choice of words there, not directly measure factor 2. If there's a correlation between the factors, or a positive covariance or negative, it's not 0. There's an indirect impact of factor 2, measuring factor 2 from these items, right? What am I saying? It measures factor 1. So it gives you direct information about what person's score on factor 1 is. But because factor 1 is related to factor 2, now if you know a little bit about factor 1, you know something about factor 2 as well. Right? It's indirect, but it's also possible.
So you are now talking about the structural model.
This is actually the structural model. This is what we would call it. The structural model is defined by the means, variances, and covariances of the factors.
So what's the difference between, because they mentioned, Brown mentioned in like the measurement model, which is this model like,
right,
and the structural model, which is factor causing other
factors,
and mediating maybe.
Yes, it's all sorts of complicated. The difference technically is this. a measurement model is the part where the factor touches the data, right? So anywhere where you see real data, that's, and the factor being defined, that's a measurement model. The structural model is what goes on with the factors, right? So in this case, a structural model would have a mean for each factor and a covariance, and what you don't see on this graph are the factor variances, right? The scale for the factors. So yeah, there are all these terms that show up out there. Structural model, something about factors. For our good for right now, for the first 6-8 more weeks, it's going to mean the covariances between the factors. Measurement model, factors touching the items, wherever the latent touches the reality. That's what, basically, where does that latent variable get defined by? Does that help? So again, the same thing with factor 2. You see the arrows. Now, one of the other things that you often see in these diagrams is where I have these lambdas. Actually, this is Lisa's. Lisa has these lambdas. You'll see a value put to each. Right? So each one, if you see this in print, you'll actually see numbers. So you put the factor loadings in the graph itself. And it helps describe what the value of each of these happens to be. And wherever you see the mu's and the kappas or covariance, put the numbers right by the arrow, and that indicates what that value is meant to be. It's one thing I realized right now as I'm speaking, I did not load in the graphics that go with each of the models from Levon, and I need to add that to our example sometime in the next week or so to show you how to do that. Because R is nice, it will plot this for you and build it so you don't have to do that. M+ will do that too, but M+ costs lots of money. So, other questions? Once again, this is sort of what people talk about as the model. Like from an actual, absolute technical point of view, it's not necessarily the model, it's sort of your representation of the model, right? And the reason why I'm saying that is because there's two terms right away that I see that aren't here, which are factor variances, which we'd often indicate with little numbers out, like error, pointing at the factor. Yes?
So if we had a measure that just is supposed to measure one, then it would just be a single factor, so just be one side of
Yeah,
that?
it'd be like one F right up here.
Yeah.
And if it was measuring all 6, it would have an arrow to all 6.
Okay.
Exactly.
Is the same as happiness example that you have?
Yeah, on my like my other class, I did a happiness example. Yeah, I think the last time I had 5 items, there was one factor measuring all 5. Right? So it'd be this one circle, 5 boxes, and then an arrow from that to each of the boxes. Good questions. Other thoughts or questions? Now again, there's great differences in how people will usually denote this. Sometimes you'll see the errors with circles, sometimes you'll see them without. Sometimes you'll see the triangle, sometimes you'll see it without. Sometimes you'll see little curved lines between the errors. That means something else. We'll get to that when we get there as well. But also the actual way that people put the numbers on varies. There was a paper back in 2002 by grad school colleagues, Rod McDonald, who tried to look at the time what people had published frequently in psych journals. And it was like there's four different types. So this is just a broad picture. What generally gets uniformly described is that the latent variables are circles, and the observed variables are squares, or triangles, rectangles. I'll say that. There's an equivalent line of this methodology that shows up in computer science, machine learning, right? Bayesian inference networks, then everything's a circle. Or everything's a square. So it's a mess. So does this help? And once again, I realize as I'm talking about this, when I say latent, I mean the factor or the trait. So I'm going to use that interchangeably, right? The trait thing you're trying to assess with square pockets.
So in homework 1, you said like the observed variables. How many observed variables do you have? You mean like the items, not the factors.
That's right. That's right. The items that are going to go help define the factor itself. Other questions?
So for Bayesian factor, at least 3 items.
Yeah, we're going to get there, but yes, the general rule, if you have one factor with no other things correlating with it, then 3 items is the minimum number of items you have. But we have there's a little bit more stipulation than that, and we're going to get to that.
Can you describe again like the one?
Yeah, this crazy thing down at the bottom?
Yeah.
And this is called the mean structure. it came in after we started using real data to do our analysis, because when we provided the computer with a covariance matrix, we just pretended the means didn't exist. That's why it's sort of added on. But what it really means is that the line that represents is the mean that goes to a variable, and the value that it gets is this mean times that number going through. No, not really. There will be, I'll show you, once we have numbers to talk about that come out of the computer, we can build it, yes. But generally speaking, the places where you see mean structures are in really complicated models that involve, some people who do longitudinal modeling involve it, but we don't, there are better ways of doing it than this, so we don't talk about it. I wouldn't worry about it too much, just show up, it's on the slide to say it could be there. So basically, in this model, what we're going to see is, I'll try to provide a little more concrete. This is not really concrete, but in the stuff that we're going to start with, all the factors means are going to be 0. So these kappa things are going to be a 0 right here, saying that mean of the factor is 0. And we're going to estimate each of the item intercepts, which is mu, which comes from that factor formula right here, mu itself right here. And so each one of those will be the factor item mean. But why it's somewhat irrelevant is this graph right here saying the item means are often discarded and not thought about because they don't tell us a lot of information about the trait. So for most of what we're going to end up doing, this is not going to matter.
So when you said that this is being used most often in the longitudinal model,
I'm trying to think of an example of where it would show up. If you want, yeah, go ahead.
Because the mean will represent, because it's longitudinal over time, so the mean is like a predictor of performance indicator across the time.
It's a little more complicated than that. No, it's a little more complicated than that. So what happens is if you want to go and estimate the factor's mean, you have to shut off one of these intercepts. You have to constrain it to be equal to 0, which is weird. Completely weird. But if you want to estimate this factor's mean, because perhaps it matters as a baseline for where it's going to go wherever else, one of these have to be shut off. And that's what the purpose of this diagram is to say when you put 0 here, the factor mean becomes a number. But the number it happens to, what that actually represents is the mean of item 1 would be the factor loading times the mean of the factor gives you back the mean for item 1.
So it's like freeing, like degree related to the degree of freedom.
Partially, yeah. It's really a way of anchoring the scale itself. You have to put a 0 somewhere for each factor that you're measuring. A 0 has to exist on the lines that are from the mean structure to it. And actually, check that. A non-estimated parameter has to exist, right? We have to set how we figure out the mean. We're going to get to that in just a minute. Yeah. So I'm going to see that. I'm going to hang on to that for just a little bit. When we get to how we have to define the factor, that's when we'll talk about that. We have to figure out what its mean is. Other questions? There are 2 types of CFA solutions that we're going to see. And actually, now is a good time for me to flip over to the example. Let me go to this example here. I'm going to stay with, to make it visible, I'm going to stay with the HTML format of this real quick. Mainly because, and actually I have the simulated data for this one, so you can actually follow along with this. I want to just kind of give you the picture of what's going on. So let's do this. So this is a survey that Lisa worked on back when she was in grad school. The paper for it's now in our shared folder on OneDrive. It starts with the last name. It's called Thompson et al. It was with the person who was a faculty member in Psych at the time. He's passed away when I was here actually last time. It's Rick Snyder, who some of you may know because of your work with Brian Cole. Brian Cole is they're at Positive Psychology. I think. So they came up with something called the Forgiveness of Situations. This is a smaller subscale of a larger survey that's called the Heartland Forgiveness Scale. And here are 6 items of that inventory. And actually, I do need to switch over to the actual numbers here. That will make me feel better about myself. Because you know it's all about me, right? So here are the items. When things go wrong for reasons that can't be controlled, I get stuck in negative thoughts about it, which is supposed to be reverse coded. So everything with an R at the bottom has that. Some of your ones that have the apostrophes, when you download it from the web, it has weird characters that show up for the apostrophes. So sorry about that. With time, I can be understanding of bad circumstances in my life. That's supposed to be positively related to forgiveness of situations. If I'm disappointed by uncontrollable circumstances in my life, I continue to think negatively about them. That's reverse coded. I eventually make peace with bad situations in my life. That's not reverse coded. It's really hard for me to accept negative situations that aren't anybody's fault. That's reverse coded. And then eventually I let go of negative thoughts about my bad circumstances that are beyond anyone's control. That's regular. So the scale are 6 items that's supposed to measure a person's forgiveness of situations. That's the trait we're trying to measure. Does that seem normal? Does that seem appropriate for those items? Does that seem? I mean, not that you represent all of counseling psych, but Michael and Craig. Anyone else from counseling in here that I forgot? No. Just look, man, close enough. Plausible. Face validity or criterion validity. But here's the funny part to me. The response anchors on the survey were 1 through 7, Likert scale, where only the odd numbers had labels. Almost always false, more often true, and almost always true. So when you get there and you see the survey, this is one of Lisa and my pet peeves about like when you write surveys, is somewhere you don't provide category labels for people. What are they going to do? Like you're not anchoring their thought about what a 2 means. It's, I guess, somewhere between more and almost, or more often and almost. And better yet, what's 4? I mean, so yeah, if you're writing your own survey items, just an easy thing to do, but make sure all of the options are clearly labeled with what you mean it to be. Even if it seems pretty obvious, probably only obvious because you've been doing this for a while. Okay, so in this example, we had the first set of packages. It needed a lot of packages. So I kept going on and on and on this. There were, I realized I needed to add more things. Most of these I'm not going to go into at all. Some of these, like knitter and cable extra, at the very bottom of this, there's an example write-up that you would write for like a journal. You're welcome to use these words. And actually in homework 3, when you do CFA on your data, you can use it too, right, to write it up. But in that example, I had to go and build tables. And I've decided to build tables out of the R numbers themselves because you can do it in R now. So it's like when I changed from real data to the simulated, that bottom example should have updated as well. Like if I rechange my numbers, it would update the numbers on the example. So it's kind of a cool thing to do. But you're welcome to use that. That's what these are. I honestly don't know most of the information about most of these packages, so I can't really tell you. To bring our data into R, we have this right here. The reading in of data for this class, for the homeworks that are online, I will give you a header file that will have this information there. So you'll download a data file, download an R script file, and if you run that, it should read the data in if they're both in the same folder. So I won't get too heavily involved in that, but if you need help getting data into R, let me know, or let Lou know. We're tech support. Lou's tech support. The first line is tech support on the second line. We can help you get your data into R. So mainly, if you want to know why I'm doing this, it's because the M+ file that was originally saved in M+ does not allow you to have labels on top of your data. It doesn't let that happen, which is crazy. So you have to give it all the labels. So I labeled all the variables. It also was a text file, so I use this read.table. So I read in all the data, but then I only select the 6 items in the person ID that we're going to be using in this example. That's what that's trying to do. You see our sample statistics, correlation matrix, means, right? We'll come back to these when we see the CFA. Variances. Now, one thing I'll note is that I had to take a variance and multiply it by a number. And that's because the default in R gives us the variances that are divided by n minus 1. And I wanted these to be maximum life with a base. Because the numbers that are going to come out of the computer are ML, which means divide by n, not n minus 1. So I just changed the denominator. I multiplied by n minus 1 and then divided by n. That's what that's doing right there. can see the formula I use for it. But here's some response distributions. These things should be normal looking. Because when we take our assumptions that the data are normal and the factor is normal, pardon me, the error is normal and the factor is normal, it means that these things should all follow the normal distribution. Do they look normal to you? Look bell curve like? No. This is actually a really good working example of items that are close to normal in quotes. This is about as good as it gets. So, yeah. So, let's get into the syntax part. This is one thing I need to work around. It compressed my code. If you look at my syntax over in the R file that starts with model 01 syntax, you'll see more spaces in between here. I need to fix that somehow. But I'll switch over to this R file right here. Here we go. So to use Lavon, we have to essentially, Lavon reads syntax of its own that's embedded in R's syntax. Right? So you already dealt with R being problematic and painful. Lavon adds another wrinkle to that, another layer. But when it boils down to it, there's a lot of parts of Lavon syntax, but we can find a way to only focus on a few of them. So bear with me here. To do Lavon syntax, we create a variable in R. I'm calling it model 01 syntax long. And that variable contains a very long text string of characters, right? So I have a quote to open up. Everything that you see in green here until the next quote is part of that Lavon syntax. It's just a very long character variable. That's all it is. Just text in quotes. So when you create Lavon syntax, you start with a quote, you hit return a couple times, and you put another quote, and then you write your syntax in the middle. Okay? The way this works, we're going to start with the idea of what we call a z-score factor. So I mentioned before we have to pick a mean and a variance for our factor when we go and do this because it doesn't exist. And the easiest one to start with is one where the mean is 0 and the variance is 1. So it's a standardized factor or a z-score for the factor. Right? So that's what we're going to use in this syntax. And it starts with every term in that model that you saw has a analogous term in Lavon syntax. Right? So that, the path diagram that had all the loadings, everything, or the actual model equation itself that had the intercept, all of those things show up in Lavon somehow. And this first long bit of syntax puts them all in here for you to see. But that being said, you don't have to put all of it in because you can rely on the defaults if you want to. I'm just doing this to be demonstrative. The first bit of syntax, can you read this on the board? Should I make it bigger? There we go. About the only thing that worked well for me health-wise are my eyes, and so I take them for granted. So please remind me that I can see really well 3 feet away. You're not 3 feet away. This first part, so in Lavon syntax, just like in R, you can put comments with the pound symbol or hashtag on a line. Right, so everything what you see here is a comment. It doesn't change the color of it because to R, all of it's a big long character string. So it'd be green. But where you see this first part here without the pound symbol in front of it, sit is the name of the factor. Right? That's the thing that you're creating. It means, in this case, situational forgiveness. Right? That's what you can name it whatever you want. But then following it, you see equal tilde. That means the thing on the left is a factor, and the thing on the right are all the items that measure it. That's right, the items that are to it. So sit is the factor. Sit 1R, sit 2R, sit 3, or sit 1R, sit 2, sit 3R. So these names on the right, Lavon is expecting these to be variable names that are in your data set. So those names have to match the names that are in your data set. Right? So if you take a look into the environment, you should see HFS situations. You see at the top are my names, sit 1R, sit 2, sit 3R, and so forth. Those are the names of the variables in the data set. So the thing on the left is not a name in the variable data set because it doesn't exist. So Lavon thinks of it as just, that's it. So what this line tells it is I'm going to create a factor with equal tilde. Each of these items is measuring that factor. And in your head, what you should be thinking is there's a factor loading attached to each of these items. This is like the line for the factor loadings. Right?
How does it know which data set to go to?
You're going to tell it once you're finished with the character, you have to call a function and you give it the data set in that function. The next bit are for the item intercepts, so those mu's. Frequently you don't include this, but the way you tell it about an intercept is to tell it the variable with a single tilde and a 1. Right, so variable single tilde 1 says this is for the intercept for the thing that's on the left of the tilde. So sit1r says estimate sit1r, item 1's intercept. That's what it's effectively saying. Later on, if you want to put constraints on it, you'll do things to the intercept, but that's what the syntax looks like. For most of the time, you're not even going to write this line of syntax because there are ways that it'll just assume, yeah, you want to estimate the intercept because they show up in all these models. The next part is, the unique variances. Anything that has a double tilde, that means the variable on either side, it's either a variance if it's the same variable. Right, so sit1r with double tilde sit1r says estimate the variance or unique variance for this item. If you were to put sit1r and put another variable name over here, it means estimate the covariance between those two. Right, so every possible part of the model shows up in this. But we're not going to get into that yet. So double tilde means variances or covariances. Now finally, one thing I will note, on the line that you see here, like line 159, I have semicolons that follow each of these statements. When you put a semicolon in your code, it means you can put more than one command on the same line. That's what that does. Once you've defined the factor, though, in Lavon's syntax, so sit up here is our factor. Lavon treats it as if it was an observed variable. I'm running late. I'm sorry. Let me just say this last thing. We'll get out of here. We'll come back to it next time. So sit up here, if we want to estimate factor variance, we do sit double tilde sit. And if we want to estimate the factor mean, it's sit single tilde. Actually, in this case, we set it to 0. We put a 0. We'll come back to that. I'm sorry I ran late. If you have questions, I'm going to stop here. Just come up after class, let me know, or email me. We'll start with the same set of syntax when we come back next time. Okay? Thanks, everyone.
Thank you so much.
I'm sorry? Oh, what's going on? Oh, this needs, I think it's looking for a new package to run. I'm not sure.
I downloaded the package.
Huh. So try the run command, see how that looks. Have you done that? Run all? Okay, now it's that. I just saw it download something.
Yeah, it did everything. And then when I click view, then that's what it's called.
While it's running, I'm going to start packing up myself here.
Thank you.
Thank you.
Where does your son go?
He goes to Lawrence Montessori.
Oh, that one. Okay.
Yeah.
I have 4-year-old.
Oh, yeah?
He goes to Braintree.
Oh, yeah.
So that's why I was wondering.
Yeah, no.
I've been there since I did school.
Yeah. I know a lot of people from Lawrence Montessori have moved to Braintree, so I don't know how that is. But Yaya's son is over there as well.
Oh, okay, cool.
Yeah, it is nice. I like it. So.
Yes.
Thank you. Okay. Yeah. So you want to tell it to
It keeps on showing every time.
Oh, it does. That's weird.
After that, then there's nothing.
Hang on a second. Let it keep going. Install it again. Yeah. So that was going to take a while, I think. Hang on just a second. So when that error shows up, it usually means it doesn't have some of the packages. Is it still installing? Or
No, it's done.
Okay. Now hit the preview. And hit yes. No. There's new. These are different packages it's trying to
No,
do.
it's RCP package.
Okay. You want to install it? So yeah, you hit yes.
اللي هو حطه هنا same package.
Yeah, it's having an issue installing the package, and I'm not sure why. Did it say anything about it?
Successfully unpacked.
Yeah. Hey. So the issue is it can't install the package on your machine, and I'm not sure why that is.
You need to update R.
You may have to update R, or you may have to point to which folder to where to install it. But let me. Sorry. Cheetah.
It's
Sorry.
okay.
Thank you.
So for that homework, so I'm using the self-regulation questionnaire.
Okay.
So the latent trait would be internal regulation, correct?
Yeah.
Okay. And then when it talks about the dimensions, does that mean like the different types? So certain items map on to like whether it's external motivation, internal
right.
motivation. So would those be
Sorry,
dimensions?
I have console at
Okay.
1:30,
No problem.
so-
Yeah, those would be the different traits that you're trying to do in the different dimensions.
Okay.
So if there's only one, it would just be that internal regulation.
Oh, okay. So then what would those